Why does adding a neutron make an atom explode? AKA understanding fission and E equals mc squared. Conceptual overview, aka what you need to know. First thing is, what is nuclear fission? Pavlov's exclusion principle, nuclear strong and electrostatic force, and what happens when a nucleus is formed. So let's begin with the basics. What is nuclear fission? Well, at an overview, nuclear fission is when a large nucleus splits into smaller nuclei. This typically happens when a neutron hits a large atom, usually uranium-235, and gets absorbed into its nucleus. The nucleus becomes unstable and splits into two smaller atoms called fission products. This split also releases a huge amount of energy, as well as 3 more neutrons, which can go and hit other uranium atoms, causing a chain reaction. But why exactly does this neutron make the isotope so unstable? The first concept we're going to need to know to understand why adding a neutron makes the isotope more unstable is Pavlov's exclusion principle. The principle basically states that no two identical fermions, neutrons included in this group, can occupy the same system. So what exactly does this mean? So no two identical fermions, neutrons included, can occupy the same system. In fission, this basically means that in the case of the nucleus, neutrons are stacked into energy levels. These energy levels act as our system. According to Pavlov's exclusion principle, if we have two neutrons that have the same spin, they cannot occupy the same system. This basically means that they cannot be occupying the same energy level, as due to having the same spin, they are now identical. And as stated before, no two identical fermions can occupy the same systems. So what exactly happens if they do have the same spin and are in the same energy level in the system? Well, if they do have the same spin and are in the same energy level, or if that level is full, the neutrons have to move faster, meaning more energy, to jump to a higher level with new spots. So in summary of Pavlov's exclusion principle's implications to fission, more neutrons equals more layers for new neutron spots, which equals to more movement, kinetic energy, which equals to more energy, which equals to more instability. So now finally to recap, neutrons in different levels prevent neutrons with the same spin to occupy the same energy levels. Because of this, neutrons have to increase their kinetic energy to increase and move up levels. More neutrons added leads to more levels needed, leads to more kinetic energy, which leads to more energy, and more energy leads to instability. The next concept we are going to need to know to understand why a neutron being added makes the isotope more unstable is strong nuclear versus electrostatic force. Strong nuclear force is basically a large force in power, but only works across extremely small distances and areas, then completely disappears. The strong nuclear force is constantly pushing against the electrostatic force. To better understand this concept, we can model this in the nucleus. We can see this in the following diagram, which shows the nucleus with the protons, which are repelled by each other due to electrostatic force, and the strong force holds it all together. So how does this relate to nuclear fission, and why the critical neutron makes the isotope so unstable? Well, more neutrons, because it's an isotope, plus the critical neutron stretches the strong force, because there's more area to cover with this energy, while electrostatic force remains the same. This new strain on the strong force allows electrostatic force to overpower it a bit more easily. And due to the extreme repulsive nature of the electrostatic force, the sheer amount of energy being produced by it is no longer contained by the strong force, making everything extremely unstable. So in conclusion to the question of why does the critical neutron make the isotope so unstable, due to the increased energy from Pavlov's exclusion principle and the strain created by electrostatic force overpowering the strong force, the nucleus splits into two smaller, more stable nuclei, plus 2 to 3, depending on the element, neutrons, and an energy release. But where does this energy come from and the original mass go? Well, this brings us to our next topic, E equals mc squared, and how the nucleus is formed in the first place. When particles are on their own, they have a high potential energy due to electrostatic force, thanks to their repulsion caused by it. However, when a nucleus is formed, particles are closer together, and the strong force has more reign because of the closer proximity and closer area to cover. This makes the particle more stable because it's kept together due to the strong force. This causes the original potential energy from electrostatic to be contained heavily because of the strong force being much more powerful compared to the electrostatic in the nucleus. And it's this right here that makes it so important. This insane amount of suppressed potential energy from the original electrostatic force is what gets released in fission. But where does the mass of the fission reactant even go? Because if you compared the weight of the reactants and the products, you'd always find that the reactants somehow weigh more than the products at the end. Well, to put it simply, the potential energy released was said mass. Why? Because less mass equals less energy, and said mass is caused by the energy itself, the stored potential energy from the repressed electrostatic force. Yes, this is Einstein's famous E equals mc squared. So increasing something's potential energy also technically increases its mass. More energy in the system equals more mass. An example of this is with the brick. If I lift the brick, I'm increasing its gravitational potential energy, which technically means I'm increasing its mass, as seen with delta M equals delta E over C2, which equates a change in mass to a change in energy. The only reason why we don't see this phenomena when lifting bricks is because that increase in mass is so small that we can't even measure it properly. And it's so insignificant that most physicists don't even consider it, especially those in the realm of classical physics. And that concludes our topic for today. In front of you right now is a visual guide for those who like to have that on hand that I made, and just note that I am not a professional by any means in physics, so if you have anything to add, anything I got wrong, please comment below, and I would love to learn from you and expand our knowledge together. I hope this video taught you something. Stay curious and keep questioning.